Okay, I'm going to go through sections 3.3 to 3.4. So first 3.3, coplanar force systems. Okay, so coplanar forces, coplanar force system or coplanar forces is basically means they lie in a plane, right, in the same plane. And when we're dealing with that, if they're in the same plane, we can, break up the coordinate systems into two dimensions. Okay, so we have just, summation of the forces in the x direction and the y direction equal to 0. So these are the equilibrium equations then. Okay, maybe tough to see, but like this is in bold, bold, bold. So these are vectors f, I, and j. Okay, and then these are scalars, and fx and fy are scalars. Okay, continuing on, looking at an example. So here's an example. You have a box weighs 550 pounds, and you look for the forces in ropes A, B, and AC. Okay, so what we can do, draw the free body diagram, of course, and that will give us the directions of our forces. Then apply the equations of equilibrium. Okay, and that's all we need to do for this. So it's pretty basic problem. But first thing is we need to break it up into the x and y. Well, first thing is draw the free body diagram, and then break it up into its x and y components. Okay, so here's our diagram, and then we can go and break it up. So in this case, we could just say for the x component of this one is going to be negative because it's in the negative x direction. The force, the magnitude of FB times the cosine of this angle, and that's what this is. And then over here, we can use the law of like similar triangles, or the relationship where the cosine of the angle is essentially just the adjacent side divided by the hypotenuse. Okay, so that's all this is. And then the other one is, now you're going to have the sine, and the direction, of course, is in the positive x direction, so it's positive. And then when you have the y components, this is going to be the sine. So it's a sine of 30 degrees because it's the vertical component, it's positive. And then we have the, this case is going to be 3 over 5 times f of c. And then now, of course, we have this weight component acting straight down. So we also have to include that in the y direction, and it's negative because it's going down. Okay. And really, it's a matter of how you draw, what direction do you draw your forces in? In this case, they're all tension, so they're kind of pulling away from the ring. And also, what did we do in this case when we drew the free body diagram? We isolated like this ring A from the system, and we're looking for the forces at the ring A. Okay. Okay. And you could do that anywhere. You can always isolate different points. You could isolate D, B, C, but A is best to do that because with A we can solve the whole system, right? We can solve what we need to find right from doing just A. All right, we wouldn't get any additional information doing these. All right, so you can go through and solve it, and it's you could do it through simultaneous equations, some form of simultaneous equations where, or substitution. Maybe you take like, since we have two equations and two unknowns, you could take and put like this part over to the other side, multiply it by 5/5. Now you have FC equals FB cosine of 30 divided by 4/5, or times 5/4 over on this side of the equation. That's equal to FC, and just take that and substitute it in for FC right here, and then now you have an equation with FB. Okay, so that's one way to do it with substitution. Right, then you can solve that and come up with the answer. All right. Okay, so here's another one, and this one expands a little bit from what we previously had. We now have a pulley, okay, and we're given a mass of a certain cylinder. So this cylinder is a mass of 40 kilograms, and that's going straight down. And what we recognize here is that this is all the same cable, so we know the tension in this cable is going to be 40 kilograms times 9.81 meters per second squared, which is a little less than 400 newtons. Okay, and we're looking for all the tensions in DE, E, A, and EB. Well, EB is going to be pretty straightforward. Okay. So looking at that, sort of visually seeing what we see. So it's a similar, seeing this, and it's a similar situation what we previously had before. So we know this force already. We can get it just from its mass or the weight of this thing. And so if we just isolate this ring E from the system, we could do the analysis right there. Okay. Okay, so here's example 2. And in this case, the author chose to use T to represent tensions. Okay, as before, we already know what this one is because of the weight, and it's on a pulley. So that's not a problem. But what we could do is we have 2 unknowns, so we can solve for those 2 unknowns because we have our 2 equations. And we can write the equations. This is negative TED, so off to the left. So that just goes off to the left, and then the 40 times 9.81 times the cosine of 30 degrees. Here's the tension in this cable, and this gives you the x component of it. And this is the same thing. Here's the y component of this cable, and minus TEA, which is going straight down. That's due to this weight, which we don't know what that is. Okay. So you can do the same thing, follow the same process. You can just take well, in this case, actually, you could solve for TED here, just straight off, and then solve for TEA right here. Okay. So you don't even need to do substitution because you only have 2 variables, 1 variable in each equation. All right. And then you can solve for those. All right. Okay. In section 3.4, this is 3-dimensional system. Okay. So we have a system like this, now more of a real world system. We have 3 cables here. We want to find out, let's say, see if it's a safe assembly or, in terms of this ring and, how it can support it. But let's say we're just looking at the chains to make sure the chains can support the weight. Now that we see we have another component in the Z direction that we have to be concerned with. All right. So here's the example. You have some force acting up on the ring, pulling the ring up, which you can essentially represent it by this hook, pulling up on it, and then the 3 cables. Okay, so here's an example now. All right. And this one's designed to lift 200 kilograms of fish. How would you find the effect of different offset distances on the force of the cables in the derrick legs? Okay. So what we would expect that if we have different distances, we're going to get some different tensions in those cables or in these supports. And what you can recognize is like this is going to be under tension, this cable, and these are going to be under compression. Okay. Which isn't necessarily always the case, but in this case it will be. Okay, so here's our now equilibrium equations. Summation of the forces equal to 0. So here's my 3 components, I, J, and K. My 3 unit vectors in those 3 directions. So all we really did was add this additional one from the coplanar forces. Okay, and with that, of course, we have our 3 equations for the individual components that are equal to 0. Right. So now we could actually, solve for 3 unknowns because we could write 3 equations. Okay. So here we go. So we want to you want to find the tensions developed in those cables A, B, AC, and AD. All right. So same old story, free body diagram, and then write the unknown cable forces in Cartesian vector form, which was, this is essentially Cartesian vector form. And then apply 3 beam equations to solve for tension of the cables. Okay, so we go through the process of doing that. And in this case, you need to see when you're talking about, the angles and how it actually is represented. So first part of this is, okay, so here's example 1. We're going to break up those vectors into Cartesian coordinate form. And we have, in this case, TB. That's just in the x direction completely. So it's just going to be TB times I. Okay. The next one is TC. So what we're doing initially here is we're basically taking and making a plane with, see this vector right here, which is a plane that's perpendicular to my z-axis. And we're taking and defining a vector here and trying to find the magnitude of that vector, right? Well, all that is that if you took this TC and made it a plane with this and this vector here, now you see we can use our basically a coplanar system or two component system. And if you notice that we start off first by coming up with the z component, because the z component is the same in both cases, right? Even if it's essentially just the z component of a vector that's in the same plane as these two, okay? Or that's in a plane that's perpendicular to the z-axis, all right? And the vector is perpendicular to the z-axis. So that's where you get the 60 degrees times TC, okay? The next thing is what we're doing is we're taking the length of this one and breaking that one up into x and y components, okay? Now the reason so here's the magnitude of that little vector here, this little one. And then the same thing here. And then we're taking that up and breaking it up into two components. And notice that for the x direction, it's sine of 30 degrees. It's negative because it's going back, in the negative x direction. And it's sine because here's my angle, and the side I care about is opposite of that angle, all right? And the other one's cosine, of course, because it's the adjacent side, and that's positive because it goes positive in the y direction, all right? So you can solve these parts and pull out the magnitude TC, and then this is what you would have for the components from this equation. And the next one is TD. Now TD is given in terms of its direction cosines, so in terms of the angles relative to each of the axes. So the first one is the I component. So this is 120 degrees. So from the positive x-axis, it's 120. Okay. So that's all that one is. And one of the things you can recognize here is that why does this work? Well, it's if you can think about it in terms of dot products, or you can just think about it in terms of two dimensions, right? You can make a plane with this vector and each of the axes. Okay. So if you made a plane with this vector, what you would find is that the angle between them's the angle that's given is the angle between them in that plane. All right. So when you do that, you find that the component of TD in the x direction is just going to be essentially the adjacent side of a triangle, and that's all this is. Okay, so this gives you that. So it's 120 degrees because that's what was given, all right, for that. Okay, the next one is in the j direction, which is essentially in the y direction, the positive y. Now you notice that 60 degrees is over here, but the angle they used was 120 degrees. So they just said, oh, since that's 60, we know it's 180 total. So we know that it's going to be 120 degrees from the positive y-axis. You could have written it as negative TD times cosine of 60 degrees, and that would have been the same. Okay. Then the last one is 45 degrees, and that's given right as 45 degrees from that axis. And then the next one is just the weight, minus 300, okay, which is given as the weight. All right. Okay, so now we write them out in terms of or adding the three vectors together to come up with a resultant. That's supposed to be equal to 0 using our equilibrium equation. And then we break it up into its components. We have TB, this one times TC, this one times TD in the I direction. Okay, so we take all the I components out, K components, and then the Z components here. Okay. Now, we could do a couple step process here. Use these two equations together, use substitution or simultaneous equations, and figure out what TC or TD is, and then solve for TC and TD with these two equations, plug those results back into equation for X, for equation 1, and then you can solve for TB. Okay, and when you do that, here's the result you get. Okay, so it's like one more step than what we previously had with our two-dimensional system. There's another, you could use like another approach would be Kramer's rule to solve these, and I'll see if I can get a video for that. Either I'll make one or find one that I think is good. Okay. All right. Example 2. Okay, so now in this case, we have a weight hanging down, our force pulling down. It doesn't really matter, weight. And then we have cable, and then we have their locations defined, right? So when we have their locations defined, we have to use unit vectors, right, to find out, to break it up into their, I, j, and k components, or the directions of the I, j, and k components, okay? So the same process here, we just have like an intermediate step. Draw the free body diagram, represent it in its Cartesian vector form, which we need to do that, then apply the equilibrium equations to solve for the three unknowns, okay? Okay. All right. So in this case, this one is right along the xy plane. We don't have a z component for A to B. Okay. And the force, it was defined as FB. Here's our free body diagram. So FB is just going to be, of course, we break this up into two components. We have the adjacent component and the opposite component here. So now you see how it's like the y component is adjacent to the angle now. Okay. Rewrite it, perform the calculation for these two parts, for the sine and the cosine, and then now you have like your FB equation. The next one is FC. FC is right along the negative z axis, so then it's just going, negative I axis. So then it just becomes minus FC times I. All right, the third one, now this is the part that's a little bit different. We need to come up with, create a unit vector, right? We need to come up with its direction. So we need to come up with those components, I, j, and k components. All right, so we can do that. We look at it in terms of its, where it actually is. Let's see, in the x direction, it's going to be 1. In the y direction, it's -2, and in the z direction, it's up by 2. So 1, -2, and 2. And then we just divide each of those components by, or the whole vector if you want, by its magnitude. So here's its magnitude, okay? The magnitude of this, or the length of this cable, all right? So then we do it, we break it up, now we have our components. All right, we can write it in Cartesian component form, all right? Okay, so we do that. We write out the individual components. Here's my i's, the j's and k's, or the x components of the force, the y components of the force, and the z components of the force. Okay, and of course, just looking at this equation, you can solve for FD right here. You can plug back into FD, solve for FB, substitute in for FB and FD, and come up with a result, right? And that's all it is here. All right. Okay, since it's positive, it's going to be, okay. So the under tension. So one of the key things is, is it positive or negative? For us, they're all cables, so we know they're all going to be under tension. Further on in the course, when we start to look at structures where we have like solid cross members, or solid members connecting different parts of our system, that it could be under tension, it could be a compression, okay? So typically with cables, we're going to draw them as away from that point, right? Because they're pulls. They're like pulling on the ring, pulling on the ring, pulling on the ring. And all you would notice that if you had drawn them in the opposite direction, you'd come up with a negative answer. A negative answer means you just drew it in the wrong direction, okay? All right, here's another one with another crate, okay? And same process. All right. The only thing different about this one now is you need to actually now we're not given the direction cosines, right? We're just going to be given their location, so we need to come up with unit vectors for those. All right. So continuing on with example 3. Okay. So what we need to do is come up with the unit vectors for these, essentially the unit vectors for the directions for the cables, right? Or what we're going to use those for is the direction of the forces in the cables, right? So if we find the relative directions of the cables, or the unit vectors representing that, that'll be the same unit vector as the force in the cable. Okay. So the first one is in the x direction. So the x direction, we have FB. So FB is being essentially from A to B. And in the X direction, if you look, maybe tougher to see this, but in this case, what the author did a little bit different. He made it like this, the 13 here, to make it a little bit easier in terms so you don't have like a fractional component. But he just doubled everything, right? So double everything and it still gives you the same direction. So instead of in the direction here, he said 2 feet, he said -4, okay? Then minus 12 instead of 6, because it's going from essentially from this point back to this plane made by X and Z. So that's the 6. So he made it 12 or -12. And then +3. Okay, so instead of like in this case in the Z direction, +3y, because this is at 2.5, this is at 4, 1.5 difference, and he just did it ×2. And then when they did the square root of this whole thing, it just came up to a square root of each of these terms squared come up to be 13. You don't have to do it that way. You could just do, what they are exactly. But recognize that even if it's ×2, it's still the same direction, right? If each of these components are ×2, it gives you a vector that's in the same direction, right? Or a unit vector that's in the same direction as what we're looking for, okay? Then the same thing for FC. In this case, I think he just did it directly. So same thing, FC goes to the plane, so it's -6. It's 2, and the here's the 2 in the X direction, and then 3 in the Z direction. So from 2.5 all the way up to 5.5. So that's 3. So that becomes 3, then 7. Okay, divided by 7 if you did, the basically magnitude of this, or Pythagorean theorem. Then f of d, we have the same thing as before, kind of doubled everything. So we have, instead of 6, f of d is from here to here, and this is going to be positive because basically it's in the positive direction. Notice the force vector drawn in this direction. So +6, and then it's right along the x-axis, right? So I'm sorry, right along the z-axis. So there's no x component in this one. That's why it's 12. So that's why you have a j component of 12. Like I said, it's ×2, and then 5 in the k direction because it's 2.5 times 2, and then divided by 13. All right. Like I said, you don't have to multiply it ×2. The author did it just to make the numbers a little bit easier to work with, right? Continuing on, all right, we write the equilibrium equation. Of course, the summation of all the forces in the vector forces, or force vectors, is going to be equal to 0. So then you can do the x components, or the i's, essentially, the unit vectors with the I unit vectors, the y components, and the z components, okay? All right. And then you can solve for the 3 simultaneous equation gives these forces. And in this case, something like this would be a little bit more involved. You could do like simultaneous equations or substitutions with these 2 equations, and you get rid of one of the variables, right? And then maybe do the same thing with this equation, substitute in, and now maybe you just have 2 variables, FC and FD, and then you can do simultaneous equations with these 2 to figure it out. I'll see what I can find. Maybe I can find something online. If not, I'll find on YouTube. Maybe I'll find something that's or create a video to show you how to do Kramer's rule, or simultaneous equations without doing substitution to solve these. But that's essentially it. When you do that, here's your result. And that's essentially it. This really is this one was the equilibrium of a particle. Okay, so if you can treat a system or part of a system as being all the forces acting at one point, then you can do it just by using those equilibrium equations. The second part of this, of course, that's kind of left out, is what if all the forces can't be represented by a point, right, or acting on one point? In that case, we have to worry about potential rotation, right? So there is a second equation for equilibrium in the systems, for our static systems, that we have to look look at that takes into account rotation. Okay, and that's it for chapter 3.